Hi, chemistry students. This is your lesson on the characteristics of compounds, in which we're going to compare and contrast some characteristics of ionically bonded versus covalently bonded compound and introduce you to the term covalently bonded compound. Now, you should be taking notes. In my class, I will be giving out some guided notes, but you can also just pause the video and take notes in your chemistry notebook. So there are two types of bonding in compounds, and the whole idea of a bond and making a compound is to achieve noble gas configurations. Noble gas configurations are very, very stable. They usually consist of 8 valence electrons, although in the case of very small atoms, it could be 2, so it looks like helium. But there are 2 different ways of achieving those noble gas configurations. First, there's an ionic bond. An ionic bond is formed when a metal transfers electrons to a nonmetal. And then there's a covalent bond. A covalent bond is formed when a nonmetal shares electrons with another nonmetal. Let's talk about each one. So ionic bonds form when electrons are transferred. So here we have our Lewis dot diagrams, and let's just look at the formation of sodium chloride. Sodium atom has just 1 valence electron, while chlorine has 7. By sodium transferring its valence electron to chlorine, chlorine achieves that noble gas configuration of 8 valence electrons. However, by doing that, sodium becomes a positive 1 ion. And again, sodium also, by losing that electron, becomes a noble gas configuration. So sodium becomes a cation with a +1 charge, and chlorine becomes a chloride ion. We've talked about nomenclature in previous videos. And it becomes a -1 anion. Because the electron has been transferred, they're not sharing, but because each of those particles is charged, positive and negatives attract each other and form a very, very strong bond. You can see down here between magnesium and oxygen, it doesn't just have to be 1 electron that is transferred. Magnesium, in transferring its 2 valence electrons to oxygen, both magnesium and oxygen achieve noble gas configuration in the form of magnesium ion and oxide ion. And again, because they are oppositely charged, they tend to stick together. Note, this is a transfer. They're not sharing. Magnesium has given away its electrons, but they stick together because of that electrostatic charge, which is very strong. And again, the ratio doesn't have to be 1 to 1. Calcium has 2 valence electrons, so by losing 1 to each one of these chlorine atoms, you form a calcium with a 2+ and 2 chloride ions with 1-. And they stick together in a ratio of 1 calcium ion to 2 chloride ions. So that's an ionic bond. The key word here is transfer. Now, covalent bonds form when nonmetals share electrons and form discrete molecules. So take a look at this right here. This is CH4, and CH4 consists of a carbon and 4 hydrogen. Now, carbon has 4 valence electrons, and hydrogen only has 1. If they share their electrons, literally between, think of the C and the H as being where the nucleus is. They've kept their electrons in between, then carbon can feel like it has 8, because these blue ones come from the hydrogen, and the red ones it already had. So it can feel like it has 8, which is a noble gas configuration. Hydrogen can feel like it has 2, which is like helium. So as long as you stay together in this CH4 molecule, then you're happy. You're very stable. You have a noble gas configuration. You can see the same thing in this picture with CF4. Notice that the carbon is the X here. The fluorine just needs 1 more. As long as you keep this pair in between, fluorine feels like it has a noble gas configuration, and so does carbon. So covalence bonds form when nonmetals share electrons and form discrete molecules. And the key word here is share. Now, ionic compounds are cations and anions in a solid repeating array. So if you were to go down really far into sodium chloride and really look at it, you would not see discrete molecules. What you would see was just an array of sodium and chlorine and sodium and chlorine. And those ions, those cations and anions, it would be usually a metal cation and a non-metal anion. And because that electrostatic interaction between the sodium and the chloride ions is so strong, all ionic compounds are solids with high melting points. Now, when you put an ionic compound in water, though, they do something called dissociate. We talk about dissolving salt in water, but there's a special term, dissociation or dissociate, and that's when a compound actually breaks up into its ions. It doesn't go back into sodium, metal, and chlorine gas. When you put sodium chloride into water, the water molecules, you might recognize these as water molecules, surround each one of the ions and break them apart within the water. That's how salt, quote unquote, dissolves. It's called dissociation. And dissociation just means you break into these ions while you're dissolved in the water. So within the water, there are these charged particles, these positive sodiums and these negative chlorines, and that's called dissociation. And that's what happens when you put ionic compounds in water. So this is another way of representing that. You start with your sodium chloride solid, and that's what the S stands for. AQ means dissolved in water. But instead of just being sodium chloride or sodium atoms or chlorine atoms dissolved in water, what's dissolved in the water, AQ means dissolved in water, are sodium ions and chloride ions. They break apart. Now, as soon as you dissolve the water, you'll go back to that solid, but while they're in the water, they are floating around as charged ions. Notice calcium bromide does the same thing, except because of the ratio, there are 2 bromide ions. And magnesium phosphate, even though it has a polyatomic, the polyatomic doesn't break up, but there are 2 phosphate ions within this crystal. So you have 3 magnesiums and 2 phosphates floating around in the water when you dissolve magnesium phosphate in water. And again, the term we use is dissociation when we put ionic compounds in water. That means breaking into ions when you are dissolved in water. Okay, now let's contrast covalent compounds. Covalent compounds are nonmetals that are discrete molecules that can be solid, liquid, or gases. It kind of depends on the circumstances whether they are held together strongly or weakly. If you have a solid at room temperature that has a very low melting point, it's probably a covalent compound. If you have a compound that's a gas or liquid at room temperature, then it's definitely a covalent compound because all ionic compounds are solids. Covalent compounds can be any. So for example, sugar is a covalent compound. But if you try to melt sugar, it'll happen pretty quickly and it'll burn. If you put it on the stove, you'll see that's what caramelization is. Salt, on the other hand, won't. So it's a lower melting solid. So you'll see sugar is a covalent compound. You see it consists of only nonmetals. Carbon, hydrogen, and oxygen are nonmetals. Water is also a covalent compound. It's a liquid at room temperature. And again, if it's a compound and it's a liquid, then we know it's covalent. Again, hydrogen and oxygen are both nonmetals. Okay, so when you put covalent compounds, this is contrast to ionic. When you put covalent compounds in water, they dissolve into uncharged molecules. So these big lumps here are the sucrose, the sugar molecules, and here's our sugar crystal. They're kind of held together. They're not, notice, an array. They're kind of just sitting close to each other like solids do. And as soon as you heat them a little bit, they'll melt. But if you put them in water, they just stay as their full molecule, okay? And they're not charged. The molecule is not charged. So we call that dissolved because they don't break up into ions. They stay as uncharged molecules. So notice the difference here. Here's putting CO2 gas into water, which is basically carbonated water. We start with CO2 gas, we dissolve it into water, AQ, we get our bubbly water. Here's sugar water. Here's the formula for sugar, and it's a solid. When we put it in water, AQ, it just means that same molecule just is now floating around in the water, dissolved in the water. So that's different than ionic, which I'm going to go back and show you one more time. Notice how these break up into ions. They dissociate. They're ionic. Covalent, on the other hand, just stay as molecules. The only thing that changes is the form. Is it a gas? Or AQ again means dissolved in water. All right, now we're going to learn a few definitions, but we're going to be doing a lab to learn more soon, but we're going to write down these definitions. So you see, ionic and covalent compounds act differently in water. And that actually has repercussions in terms of whether or not the solution will conduct electricity. Solutions that contain ions, ionic compounds, are called electrolytes because they can conduct an electric current. Ionic compounds form electrolytes when they are put in water. Solutions that do not contain ions are called non-electrolytes because they cannot conduct an electric current. Covalent compounds form non-electrolytes. So sugar water, as we're going to see in a upcoming lab, is a very poor conductor of electricity. Very little is conducted because there are no charged ions. So here's a summary that you should know. Ionic compounds consist of a metal cation, or we've talked about this polyatomic ammonium, transferring electrons to non-metal anions. They are solid arrays of ions. They have high melting points, and they can conduct electricity when dissociated in water. That's called electrolytes. Covalent compounds consist of two or more non-metals sharing electrons. They are discrete molecules. They can be solid, liquid, or gas, and they do not conduct electricity when dissolved in water. They are called non-electrolytes. So that's your lesson. Hope you enjoyed it.